and custodians of this tens of thousands of years. So we pay their respects to their elders, past, present, and emerging. So it's with great pleasure that I can introduce Xin Wang, who's visiting here from the Chinese Academy of Sciences. He's actually going to be a long-term visitor here for at least this year. And so he's been here since January 15th or so. And I'm really excited that he's here because we have many research interests in common. One that's close to my heart, subduction zones, but also gas and many different things. And so if you are interested in meeting with him, of course, he's here this year. You can contact either one of us and arrange a meeting. That's why I didn't put together a schedule for today, because we have him around, lucky to have him around. Xin did his Bachelor of Science at Jilin University, and then he went on to do his PhD at the Institute of Geology and Geophysics at the Chinese Academy of Sciences. He was also a visiting researcher in Singapore during part of that time, and then he following his PhD, was there as a research fellow. And then he moved on to Caltech for a couple of years as a postdoc there before going back to the Chinese Academy of Sciences, where he's now associate professor. So please welcome him, and we'll hear more about subduction zones. Thank you.
Thanks for Megan's introduction. It's also my pleasure I'm here to give this presentation. So today I will mainly focus on the subduction zone, and mostly from a seismological point of view to see how can we understand the energy and also the material exchange between the subduction zone and the mantle region. So this work mainly done with some of my colleagues in Institute of Geology and Geophysics, Chinese Academy of Sciences, and also with some collaborators from GSC, Caltech, and also the EOS. So I will first start from this very basic figure. We know that the subduction zone means that one place subducts to another. It's one of the most dynamic region in the Earth that exchange the energy and also the materials between the surface to the deep interior. For the subduction process, basically we have a oceanic lithosphere and seeping into the mantle. The oceanic lithosphere itself consists different lots of the material, for example, the oceanic crust and also the oceanic mantle. And on the upper part, we can also have lots of the sedimentary materials here. So when this kind of the different kind of materials going to the deeper Earth, it will create a lot of the significant velocity contrast between the subducting slab and also the surrounding mantle. So in this talk, I will try to define two words here in my talk. It's not probably not that good enough, but I will simply to use the upper interface to indicate the boundary between the slab and also the surrounding mantle, and also the slab lower interface to define the boundary between the subducting lithosphere and also the subducting the underlying asthenosphere. So there's lots of the complex and dynamic interactions at these boundaries. So for example, in this region, we have lots of the slab dehydration processing and also lots of the partial melting, which is very important to understanding the volcanoes in the upper plate. And also potentially we have lots of some partial mass as the boundaries of the slab lower interface and asthenosphere. And also the earthquake, because that we know that megathrust cause lots of the devastating earthquakes. So for my study, I'm trying to use seismological methods to image this kind of structure, the upper one and lower one, and see how this structure complexities can enhance our understanding of the megathrust behaviors and also the dynamics between the slab and also the surrounding mantle. So this is mainly the cartoon view or just a sketch figure to show the subduction zone. But if you go to the seismology part, so when we mention subduction zone, most of us will think about this kind of figure, the tomography studies. Basically, in seismic tomography, we are trying to using the arrival time and also the waveform to image the with high velocity and also the low velocity beneath the Earth. Typically, we have a high velocity for the subducting slab and also the low seismic velocity. Here showing the right, show the surrounding mantle. The higher velocity typically means the higher velocity, the colder region. Basically, it's just a temperature. It's first order to reflecting the geometry and also the temperature of subducting slab. But today, I will go to a little bit into details to this kind of subduction process. So the left figure shows the typical the seismic tomography studies. Basically, we use the seismic data to derive this kind of small variation of the subsurface structure, the slab, and also surrounding mantle. Actually, if the velocity contrast is very strong, they also may see this kind of the seismic discontinuities related to the subducting slab. For example, if there's lots of the material contrast between the slab and also surrounding mantle, and also if there's some partial mass. To the right figure shows you one of the typical reserve function image in Japan subduction zones. Basically, this is Japan Trench, and this is Japan subduction zone. By using the reserve functions, you can see lots of this kind of the blue or red discontinuity signals here. For example, for this case, this is subducting Japan slab and Pacific slab, and on the top we have two groups of signals. On the bottom, we also have a very coherent negative signals here. So zoom into this figure, basically the upper one is the blue and white means the negative and positive seismic discontinuity related to the slab after interface. This very related to the composition of the slab and also the dehydration processing of the subduction zones. So this upper interface is very important for us to understanding how many percent of water have been dehydrated in this region, and also the entire water cycle in subduction zone process. In addition to the upper one, in the lower interface, we can also see that there's a very coherent seismic signature here. It indicates the negative seismic discontinuity, basically the velocity decreasing sharply at this region. For this region, we have this discontinuity mainly due to the existence of the partial melts. For example, if we have some partial melts here between the mesosphere and asthenosphere, then it will create this kind of the sharp boundary. So the discovery of this sharp boundary is very important for us understanding how many percentage of the melts are here and what's the melts effect on the slab and mantle decoupling effect. Basically, this is just a basic concept of subducting interface I'm trying to discover in this talk. This is just the baseline for understanding what's the basic seismic structures here. So we have typically when there's a high velocity subducting slab, it will create a group of discontinuities at the top. This may relate to the composition and also the dehydration processing. And we also have a negative discontinuity here. It may relate to the partial melt beneath the slab. So, but in real case, the seismic structure can be real complex, especially if we look at this structure by using different kinds of methods. So, for example, this is one of the case in the Vancouver region, the North American Trench. So basically, this is North American. This is Vancouver. So to the left figure shows you a typical high seismic imaging by using the receiver function study. So we see lots of this kind of the red and blue seismic signals, including its multipliers. Basically, we can constrain these two interface and also the velocity VP-VS ratio, this proportional ratio here to indicate how many water percent, how many melts are here. So to the right figure actually shows you one of the active seismic source imaging profile here. Almost exactly the same profile, but shows lots of different structures here. One of the most important features is that you see lots of the reflectors here. If it's compared to another regional seismic tomography, define this is the Moho boundary here. Basically, all the reflectors are located above the slab Moho and also the slab top. So they think probably there's reflectors here. So it's really depending on how detailed structure you are looking at them. Then probably you will get very different ideas than what's the signals showing here. So this is just a very simple summary figure about our understanding of the slab upper interfaces. So this is the basic figure. We have the negative and positive seismic discontinuity to define this kind of low velocity or oceanic crust potentially, including loss of the water here. But depending on whether you have additional seismic discontinuities here and also the relative location of this kind of discontinuities, you'll probably have lots of different explanations for this seismic observations. So this is mainly about slab upper interface. If we go to the deeper depths, go to the lower interface, there's lots of the debates on the slab lower interface. This is the figure I just show you in the Japan subduction zone. Basically, we see this kind of the seismic discontinuity in the negative one. in this figure, in this results, they only image a single seismic discontinuity. So they define this is the changing from melt-rich zone to a melt-rich, meltless region. But if you go to another study, for example, this is the active seismic source study in the New Zealand. So basically, this is New Zealand, and by using the active source data, they also see lots of the slab related to discontinuities here, including to the upper one and also the lower one. For the lower one, they image the group of seismic discontinuities at the bottom. So basically a negative one and also a positive one. So they define this to a two discontinuity as a melt-rich zone compared to a melt to meltless layer. So this is how the difference in understanding the slab lower interface. If we look at this question to the global, actually there's lots of interesting phenomena here. To the left figure, I show you these two studies, one in Japan subduction zone, the other in the New Zealand subduction zone. In both cases, they observe this kind of distinct slab lower interface structures, and both subduction zones are very old and cold subduction zones. If you go to the other side of the Pacific Ocean, for example, the North American subduction zone and also the Middle American subduction zone, actually there's lots of the debates on whether we have a slab lower interface here. So before subducting, this ocean, this normal ocean, we have this kind of distinct lithosphere asthenosphere boundary here, and also this kind of melt region as the boundary between the lithosphere and asthenosphere. But when the subducting start going down, actually there's lots of debates. For example, in this case, they didn't discover any features here, but in this case, the different studies propose the different ideas. So on the in the old and cold subduction zone, we have this kind of distinct slab interface, but in the warm and hot subduction zone, warm and young subduction zones, we didn't find this kind of the observation. So why we didn't find this seismic structure is due to seismic imaging, or it's related to the age-dependent factors in controlling the formation of this seismic discontinuity. These are mainly from the seismic imaging point of view. The subduction interface is also very important in understanding the megathrust here. So basically this figure, we know that most of these kind of the big earthquake, magnitude 8 and 9 earthquake occur in subduction zone, mainly on the megathrust, the upper interface. So we need to have better understanding the geometry and also the physical properties of this slab upper interface, because it's very important for us to understand how this megathrust earthquake ruptures and also the related seismic hazards. So in this talk, I will try to show you two recent studies. One of them from seismic imaging. By using seismic imaging from density, we try to provide evidence for the existence of the slab lower interface in the young slab at Cascadia. The other case study is from in the Sumatra region. By using the relocated seismicity and also their focal mechanism solutions, we try to rival the plate interface geometric complexity, and which is very related to the coupling and also the rupture extent of the big events. So in the first, we'll go to the in the next, we'll go to the first stories first. So let's buy to this figure. To the left side shows you the old and cold subduction zones. We have image distinct slab interface here, but to the right side, we have lots of debates. For example, these two studies provide very different ideas whether we have slab or interface. So if we look at this figure, Cascadia is one of the really important region to resolve this puzzle, whether we have or not. So let's look into the Cascadia subduction zone. To the left figure shows you one of the tomographies in Cascadia by using both the ocean, the OBS data, the seismic data in the ocean, and also land revival of trench parallel low velocity zones here. Basically, if you put into a cross-section view, from cutting from the west to the eastern side, you can see this blue one indicating the high velocity slab, and you have lots of the low velocity zone just beneath the slab. So they just propose the idea, probably there's lots of the melt beneath the subducting slab. So the melts accumulate as this kind of the region. So we have this kind of the we have imaged this kind of the low velocity zone. Basically, the purpose there should be had, but in seismic tomography study, they don't have such resolution. To the right side shows another type of study, basically using the same data, but they mainly argue that the low velocity zones here is an artifact caused by the seismic imaging. Basically, they conduct lots of synthetic tests. For example, if we have input model of high velocity slab, so when we do the inversion, if we use a good starting model, then it will roughly revival the slab geometry, but no artifacts here. If we have different assumptions in station corrections, they will introduce lots of this kind of artifacts, which can be an artifact in the imaging. So in my case, I try to figure out how can we really image this kind of the structure or not. For me, I use the seismic stations deployed in the Cascadia, mainly in the Oregon region. So this is the basic map our study area, the Huanafuca plate subducting to the North American plate. This is the Oregon region, and in this region we have very dense seismic observations. So here the red dots shows you the blue dots shows you the broadband seismic station deployed about 30 or 40 years ago. The stations spacing about 5 kilometers apart, with observations of 1.5 years. And with development of this kind of the short period node stations in 2007, they redeployed the seismic stations here with a very dense spacing, 500 meters, but the observation period is only 1 month. So to resolve the seismic discontinuities, here we're using the receiver function imaging. Basically, it's mainly using the Kali seismic earthquakes here. For example, if we have earthquakes here, and if we have seismic discontinuities here, we have lots of the conversion spaces across these discontinuities. Basically, we have this lots of seismic signals here. Then we can use these seismic signals to constrain the depth and also the velocity properties related to the seismic discontinuities. So actually, this is not this is a very old data. You can see that this data was deployed in almost 30 or 40 years ago. So there have been lots of studies trying to use this data to look at the slab structures here. For example, this figure shows you one of the classical study. Basically, in their study, they observe this kind of the inverted mantle here. This is related to the standardization of the fault mantle. In this figure, we can also see this kind of the low velocity subducting oceanic crust, but we have lots of the signals here. It's really challenging to see whether this structure, the signals are real structure signals or they are caused by the multipass. To the right, the figure just shows some of the recent studies by reanalyzing this data. For example, the upper one shows you the broadband receiver function imaging by using direct phase and also the depth phases. Also, it's really challenging to see the slab structures here. And also, this one shows you the results by using the short period node stations. Basically, we can see a group signals here, but without this kind of the blue and white line, it's really challenging to see which one is slab mantle and which one is slab archer interface, and also what's the structures here. We don't know. This is mainly due to actually in the receiver function study, we use seismic deconvolution. There's lots of non-uniqueness of deconvolution due to noise and also the local scatters. So for example, for this seismic station, it deployed only for 1 month. If we don't have enough earthquakes, that means we have insufficient. Then due to the noise and also local scatters, we are really challenged to see this kind of the reliable structures here. So in my work, we first try to develop a new method by taking advantage of this kind of the dense array. If we have a really dense array, then probably we can use in the coherent features recorded by the dense array to extract this kind of coherent structures by suppressing these scatterings. So basically, we call this kind of the array-based receiver function imaging. So next figure shows you just a comparison between our study and also the previous one. Basically, this is the broadband results, and also this is the short-term results. After applying this kind of the array-based receiver function imaging, we see lots of the coherent features here. For example, very coherent blue features here, and the red features here, and another blue features here. To the lower side, we show the probability density function of our obstinate feature. That's the reliability of this feature. We can see lots of features have really high probability density function, means that they are very reliable. So by using this kind of new imaging method, we can better to suppress noise and get this kind of structures here. We also using the earthquake coming from different direction to get images and also compare with our results with regional tomography studies. Basically, these two panels shows you using the earthquake coming from southeast direction, basically this direction, and these two panels shows you the results coming using the earthquake coming from northwest directions. So in both of these kind of images, we can see lots of the positive signals at the top, probably related to the sedimentary layer, but at depths around 20 to 80, there's lots of very coherent and dipping features here. For example, this one, this blue one, and similar this blue one. Also the very coherent the red one, and also the blue one here. Here the dashed line is the slab top interface from the slab slab 1.0 model. You can see that this kind of blue feature is very coherent with this very correlated with the slab 1.0 model. The lower one shows you the seismic tomography studies. Basically, we can see this kind of the high velocity subducting slab. And if we put all these signals on top of the seismic images, we can see lots of they are very coherent. For example, these two, the first blue and red, it's roughly define the low velocity zone here, probably related to the subducting oceanic crust. From this kind of the red to the blue one, it's very corresponding to this kind of the high velocity, probably subducting slab mantle. So we think probably the lower one, this kind of blue one, it indicates the slab lower interface image in this study. We also compare our studies with offshore data. So the red figure shows you one of the results by studying the lithosphere asthenosphere thickness in the ocean. So basically, different color means the types of the LAB thickness here. To the right side, they show the roughly estimated slab thickness by using the slab top and also the lower boundary. We can see they are roughly consistent. Basically, we are trying to fill in a gap between the west and eastern side of this study, trying to see actually we can really image this kind of slab lower interface here. It's just the ongoing of the lithosphere and asthenosphere boundary here. So in addition to see this kind of feature, we also try to estimate what's the seismic properties related to this feature. Basically, what's the sharpness of this discontinuity and how many velocity perturbations here. To achieve that, we're using the multi-frequency receiver function modeling approach. Basically, if you have very sharp boundary, for example, this black one, by using different frequencies, you have almost consistent amplitude. But if you have a small seismic discontinuity, for example, caused by the temperature alone, then by using different frequency, you have very different amplitudes here. So by looking at the real data, if we look at the real data, for some of the discontinuities, actually, with the increasing of the frequency, the amplitude is decreased very quickly, very similar to this kind of small discontinuity. But for this one, the purple one, this indicates the slab lower interface discontinuity. By increasing the frequency, the amplitude are almost similar, indicates that's a really sharp seismic discontinuity. So in this case, probably we need to consider the melt to explain our observations. So we just simply transfer the velocity jump to the melt fraction. Of course, there's lots of trade-off assuming what's the melt geometry here, but roughly it's corresponding to 1 to 4% melt fraction here. So if we have this kind of the melt fraction, it will reduce the viscosity of this layer, then probably will impact our subduction dynamics. For example, just about the left figure shows you the one studies by including this kind of the low viscosity layer result. You can see that the subduction with the subduction, the geometry of the slab, and also the subduction speed, and also the mantle, the velocity of the mantle block change significantly. To the right side, just show you how this kind of the very thin layer can affect the earthquake cycle. For example, for the left figure, we don't consider this low viscosity layer, but for this no consider, but for this figure, we just consider the other parameters are same. So we can see the deformation pattern for this kind of the earthquake cycle are really different. You have lots of the horizontal motions here, and also very different amplitude of this kind of the viscoelastic relaxation here. So when we have this kind of layer, it may influence the subduction dynamics and also the earthquake cycles. So a short summary for this study is that here we present seismic evidence for melt-rich slab LAB. So there's a slab lower boundary here as base of the young slab Cascadia subduction zone. We think probably it's very common just before and after the subduction, and this layer may significantly influence the subduction dynamics and also earthquake cycles. Of course, there's lots of questions here, so I just leave here. But if I have time in later, probably I will try to discuss more details. What's the question here? For example, whether we should consider the boundary or the zone, or it's really a system, and how these melts were formed, and also we observe lots of the strong lateral variation and how this lateral variation influence our earthquakes, the megathrust behaviors here. So this is just from the seismic imaging point of view to trying to understanding the slab interface here. So in the second part, I will try to jump from the seismic imaging to the earthquake style studies. Basically, these two studies are all focusing on the slab interface. But this one focuses on very large scale. But the next case, we will try to look at very detailed interface geometry to see what's the relation of this kind of 3D geometry and also the megathrust rupture behavior. So let's from this figure, so that in subduction zones for the slab upper interface holds lots of the megathrust behaviors. So, but for each earthquake, they have their distinct rupture behavior. For example, this is Sumatra subduction zone. Over the past 20 years, we have lots of the big earthquakes here. For example, 2004 Sumatra 1, 2005 Nias, and 2007 Bengkulu, and also the Mentawai tsunami earthquakes. We can see that different earthquakes have different rupture patterns. So what control the spatial variation of the co-seismic ruptures here? So one of the key question is one of the way to understanding the structure, the lateral variation of this kind of a co-seismic rupture is trying to understanding what's the geometry of the slabs here. So we can use lots of methods to try to look at this question. For example, one of the classic way is trying to conduct the seismic reflection imaging or by using the ocean bottom seismometer. So basically, this just shows you a figure from previous seismic reflection studies. We can conduct very high resolution reflection studies and to see what's the structural variation of slab interface. We found that there's the topographic height for slab interface just in between the 2005 earthquake and also above the large historical earthquake. We think probably this kind of structural variation control the lateral variation of the megathrust behavior. But for this method, it's very hard. It's very expensive, and it's really challenging to apply this method to all the regions to say what's the lateral variation of structure. Another way is trying to using the seismicity. We know that earthquake occur on the faults. So if we have a good constraint on the earthquake location, for example, the horizontal and also the deep. In some cases, if we can also constrain the deep angle of the earthquake, we can use seismicity to delay into the fault geometry here. But in most cases, for example, showing here, we need really dense observations. For example, this is in California. But if we go to the subduction zones, in most cases, we don't have such observations. So we may only rely on the global seismic observations. This just show you two global seismic catalog and also one local catalog. So basically, if you look at this kind of global catalog, we can roughly see the slab here, but really challenging to see what's the structure variation here, and especially how reliable for the locations. If we even go to a local catalog, we can see that roughly we can define the slab geometry here, but due to the location uncertainties, it's really challenging to see the structure variations in detail. This is mainly due to the limitations by using seismicity to deal into the slab geometry. So over the past few years, we try to improve this study by using the global seismic data. So basically, we try to conduct lots of the global seismic modeling by using different parts of seismic waveform, for example, the body wave, the surface waves, and also P and S waves to conduct individual studies, for example, the focal mechanic inversion, surface wave relocation, and also the high frequency backspaces modeling to better constrain the locations. Just a figure to show you what's the difference between our study and previous one. So after relocation, this is almost exactly the same data sets. We found that actually the earthquakes are very clustered. So for example, in this case, this profile, we found that earthquakes are clustered into this region and also this region. We can also very constrain its deep angle here with uncertainties only less than few degrees here. By the way, there's a lot of seismicity here, but all the earthquakes are located almost at a similar depth and also the horizontal locations here. So it's just look like two data points here. So we use this measure to particularly look at the Mantella seismic region because this region was recognized as a seismic gap. So in 2004, 2005, all this section have been ruptured. In 2007, part of the regions have been ruptured. There's also a high coupling region unruptured. So why this earthquake didn't rupture all the way to the trench and to the left side? So what control the spatial variation of the co-seismic ruptures here? So we conduct detailed study on this kind of the earthquake locations and also focal mechanism by using the global seismic data. So in the next, I will show you three profiles. One cutting through the center of the co-seismic slip of 2007 Vancouver earthquake. The other one located to the western side and one located to the eastern side of the profile. So basically this figure, the upper one shows you our results, the middle one shows you the USGS catalog, and lower one shows you the GCMT catalog. So you can see that from the global catalog, it's really challenging to see the detailed slab geometry, but in our cases, we can see that lots of the earthquakes are very well constrained and also are very well clustered. So especially for the GCMT solution, there's a strong trade-off in the deep and also the depth. So that's why we have this kind of shape. Actually, it's not real. It's mainly due to the trade-off in the study. Actually, this earthquake are well clustered. So we can use this to constrain the slab geometry here. The previous one shows you depth, and this figure shows you the deep angle variation. So for example, the GCMT have lots of the trade-off in terms of depth and also deep angle. For our study, we can well constrain the deep angle of earthquakes, and we can also compare our constrained deep angle to the co-seismic rupture of the last earthquakes because we think that typically a large event may have a really constant deep angle. So we can see that there's lots of the variation for the deep angle here. For example, jumping from this large event to the plate interface, the deep angle changes a lot. Also for this event, the deep angle changes a lot. We think probably this deep angle changing has some implications for understanding the rupture behaviors here. So of course, there are lots of the local variations. So if we compare these three profiles, I just put here, then you can see different color indicating deep angle from different profiles. So you can see that there's lots of the variations here. Basically, we can use all these locations to constrain the 3D geometry here. We're using our relocated catalog and also their deep angle. So the dots here or the circle here roughly represents the rupture dimension of this kind of medium or small earthquakes. We also use the seismic reflection profile from industry companies. Then we combine to derive what's the 3D geometry here. So roughly, we can see the geometry here, and this red patches shows the co-seismic rupture of the 2007 Vancouver earthquake. You can see that it's almost within this kind of rupture. So probably thinking that the local variation of the structures control the rupture extent of the megathrust. So just some takeaway message. So after relocation, actually, we found that most of the earthquakes are defined two clusters, one in the up deep region and the other one located at down deep region. So The down dip region may indicate the bending because we see lots of deep angle change from the megathrust to this cluster. For the upper cluster, actually the deep angle are consistent, but probably they just indicate some material or fraction changes from this side to this side. So the overall, the 3D velocity, the 3D variation of the plate interface, controlling the rupture extent of the megathrust rupture behaviors here. So I will try to start my presentation with this figure because over the past years, I'm mainly in China, in Singapore, or in Southern California. But nowadays, I'm trying to shift to Australia because my wife just moved to Australia to work last year. So in the next few years, I will stay here very often, and I have lots of interest, for example, the subduction zones and also induced seismicity and also the canals. So if you have any interest, we can probably working together to figure out some very interesting questions, and really happy to collaborate with anyone here. So thank you for your attention.
Very great talk. Do you have any questions?
I wonder about the moment and so the solution that you saw in the last two slides. I saw here.
Probably this one.
There are relatively shallow here, from 10 to 30 kilometers or something.
Yeah.
So what do you do to constrain the so in compared to traditional methods, what did you do to really constrain the
Depths.
the depth and also the geometry of the events?
The depths mainly constrained by using this relative high frequency depth spaces modeling. So the depth spaces that we know that if there's an earthquake, there will be direct phase go to a teleseismic station. So there are also a group of phases just reflect at the surface, then recorded by seismic station. So the read paths for these phases are very similar, except for this very shallow region. So basically, this is P phase and this is depth spacing. So we can use the arrival time and also the shape of this depth spacing to very well constrain the depths of these earthquakes. So here, by only using the modeling, we can narrow down depths to just less than 1 kilometer. So here I mean the depths on Earth mainly because I also consider the shallow velocity, 2D velocity variations here. So it's the depth mainly constrained by the depth spaces modeling. For the deep angle, actually I didn't talk too much here. So we found that in previous studies, if we only using the, for example, the P and SH waves in the inversion, there's lots of the trade-off. That's very similar to the GCMT solution. You'll see that the deep angle and depth movement trade-off. But if you can include more phases here, then you can better constrain the deep angle with just a few degrees of uncertainty.
Basically, you are using body weight to constrain both of them.
And yeah.
I'm sure you remember well the study of Cambridge in 2009, but were you talking about melts or you frozen melts this site with the solidified? So could you tell if this is really melt of a given volume or it's just a different composition?
I think it's for me it's really hard to estimate what's volume and also what's type of melt, whether any volatiles within that. Mainly because for this study, we can only constrain the velocity reduction and also the sharpness of this continuity. So we just interpret in general, probably related to the melt. If we consider different volume and also the geometry of the melt friction will be changed. But in one of our recent study, we're trying to incorporate more data and more constraint to constrain the geometry of the melt. That's what's the aspect ratio of the melt and also any volatiles within the melt. Probably if I have some time, we can discuss that. I think that's really interesting stuff in the volcano region. Yeah. But in this case, we just don't have that resolution and we didn't dig into too much on that.
Very similar question about the melt. So for some people, concept of partial melt of the mantle is still very controversial.
Mhm.
So I just wondered your opinion on how, essentially, how confident are you that it melts and it can't be
Okay.
explained by something else?
Yeah, so actually in our explanation, we just borrow, borrow some idea from previous studies to explain to the males, of course. For example, anisotropy or other effects may also contribute to the velocity reduction sphere. So for this study, we think the sharpness is about constraint. For example, in our inversion, we found that the sharpness is this discount is very sharp. For example, just less than 3 kilometers. So probably about the melt could be the easiest way to explain the observation. Yeah.
So I have a question on a very similar thread. So if you
And not you.
Yeah.
melt, you actually mean that it is still molten or that it's a former melt? And if it is still molten, how metrologically, maybe the guys at the front can step in and help. How does that actually work? How do you get a melt that's going to higher pressures?
Yeah, that's a really good question because when I look at this figure, so we always think that the compression melting, so with the depths going to the ups, then melts come out. But in this, let me go this figure, sorry. They try to explain this actually at very deeper depths. They think that when we have this kind of going down, the pressure increase, so the melt should be solidified in most cases. But where we still have some melts, so I think one of the model we are thinking that probably there's lots of the melt. Or what was this? How to say that? Probably just within the asthenosphere. Then we have this kind of the boundary due to the permeabilities of this boundary, then melt just accumulate at this boundary. But eventually, probably the melt will migration. If it's going up, then accumulating the trend is going down, just solidified to the. I don't know. yeah. So I think really a good question. I just realized probably sometimes I should give you some of our recent research on the volcano region. In that case, we have lots of confidence for the melt and also the geometry of the melt and also the volatile sphere. So that's a really interesting story. Yeah, if I have time later.
A couple of questions, if that's okay. So do you, from your results, can you go back to the Bostock
Yeah.
kind of review paper?
Mhm.
So can you reiterate which one your results help support?
Can't we our results mainly start to this kind of model. Yeah, but I think we have different types of model mainly due to the resolution increasing. So basically using the seismic reflection, we see lots of reflectors. So for the typical passive source seismology with zero function, we can only see these two structures here. So for me, I most prefer this kind of model. But if we have more data, especially for the active source data, we may look at this kind of structures here. So I think it's really general that nowadays, if the passive seismologists and also the active this kind of seismologists looking whether is that possible for us to sitting together look at the same structure at the same time to see the puzzle, what's the real structures here? Yeah.
And then I guess in contrast, since this is the warm setting,
Mhm.
and in my head, I imagine it quite different than the Kawakatsu study where you have
Yeah.
a much colder, older slab. And are you, what's the resolution on here versus the cold slab where I would imagine that those discontinuities could be much sharper because of the thermal properties. of
Yeah,
the
yeah.
slab.
I think the resolution almost similar, yeah, because they're using the almost similar kind of the data set. I mean, in terms of the frequency bands, yeah.
But even with the sharpness of those boundaries, I'm just imagining in the cold slab setting, that the velocity contrast is going to be more significant than it is in the warm setting where the contrast may be more muted.
Oh, actually, from observation, they're almost similar.
Really?
Yeah, yeah. So that's the one thing I'm really interested in. I'm always thinking that probably due to the age, the colder region, then we have a sharper one. But actually, if we look at the sharpness, also the velocity reduction, for these two studies, they are similar. In addition to that, if we look at the oceanic laser sphere thickness or the seismic properties related to that, we know that there's an age dependent for the oceanic laser sphere thickness, but if you look at the velocity reduction, they're almost similar. Yeah. Probably they just don't have that resolution to resolve the difference.
Yeah, actually, one question not related to the subduction system at all. But since that there's still time, so can you actually go back to the Cascadia study? We're showing, I think, earthquake coming from two different directions, and showing that kind of a here. So something caught really my eyes on the figure on the left hand side. You see this kind of blue interface actually in the within the upper plate. This one. Yes. So what are this? Which is completely gone on the right hand side.
Yeah, actually, to be honest, I don't know what's the structures here. So for this, I'm not sure this mainly due to the 3D scattering effect. Yeah, so because this just very coherent and also coming from another directions. So in these two studies, they are still the two-dimensional work. So probably in the future, we can look at 3D to see whether some of these features caused by the 3D scattering effect, just coherent scattering features here. Yeah.
Okay.
Just one quick one. So on one of your previous slides, you talked about the sedimentary layer on top of the slab.
Mhm.
And it looked in your seismic image that it was about 10 kilometers thick. So is that compatible with the sediment thickness going into the subduction zone? Or I'm wondering how well resolved that kind of layer is.
You mean for these two layers?
For the top layer, so the blue,
This
slab
one.
top. So on one of your earlier slides, you labeled that as kind of sedimentary. I know there's a lot of sediment going into that subduction system. It's really about 10 kilometers. So is that
No, I was thinking that this probably related to the sediments, the upper one. So for this, I think mainly still the oceanic crust there. So probably they don't have too much sediments here.
okay, but there is 4 to 6 kilometers or so of sediment going into that subduction.
4 to 6, sorry. Let me see whether I have some bigger. No, I don't think we constrain the sedimentary here.
Any good question? No. Thanks, Xin, again, and thank you very much for the seminar.
Thank
Gift
you.
From RSES.
Well,
All
thank
right.
you. Yeah. Thank you.
And don't forget that there's tea after this, so please bring your own mug, and then what it is.